Excuse me. Okay, how about this? How about the derivative of, what if I have the derivative of a constant times a function? How about that guy? Well, remember, push meet shove if I'm proving a derivative. I take the limit as h goes to 0. Every time that I come up with a new derivative rule, I have to prove it somehow. I can prove it intuitively, or I can prove it algebraically, or I can prove it graphically, but I have to prove it. So that's what we're going to do. This is the limit as, okay, now let's think. This is just a constant, so it's along for the ride. So I'm going to have the constant times f of x plus h minus the constant times the function, right? Because really, think of this really as being like a g of x, right? It's its own, it's a term, it's its own function, right? I don't want to have to rewrite this as g of x plus h, because that's what it would be. All right, so all divided by h. Now this is equal to, look, what do you notice there? I've got a constant. This is the limit as h goes to 0 of the constant times f of x plus h minus f of x all over h. If I suck the constant out, I'm going to get the, remember I'm allowed to do that. That was one of our laws of limits. So this is the constant times the limit as h goes to 0 of f of x plus h minus f of x all over h. And guess what this big bad boy is? This guy is f primed of x, and the constant is just along for the ride. In other words, the derivative of a constant times the function is simply the constant times the derivative of the function. Now, think about what that means. If I'm, let's say that f of x, for example, if I say, I guess that's there for, sorry, there we go. For example, what the hell did g come from? For example, if I say that f of x is equal to 19x squared, right? Well, that simply implies that f primed of x is equal to 19 times the derivative of x squared. Now, you don't have to go through this process. You're going to do this in your head. It just means that this constant right here is along for the ride. So I get 19 times 2x, which is effectively known as 38x. My derivative's done. Constants are wonderful. They're just, they float along with us, and they do all sorts of good things for us. Excuse me. Okay, so let's talk about another rule. Let's see. This is a rule, so this should probably have, I forget what number we're on. I think we'll call it 5. I think we're on 4, but we'll call it 5 anyways. All right, how about this guy? How about the derivative of a sum plus g of x? Now, hopefully your brain is starting to see how inextricably linked limits and derivatives truly are. And you may remember that the limit of a sum was the sum of the limits. All right? And you'd be right. However, let's do a quick proof. Now, think of this as its own individual function. Okay, so we've got a function here. So I'm going to try and show what the derivative of a sum is. Again, our intuition, our instinct is probably saying, well, duh, Ripley, the derivative of the sum is the sum of the derivatives. But let's check it out. Well, this is f of x plus h plus g of x. Whoops, plus h. That should be g of x plus h. Right? Wherever I see an x in this thing, I just stick an x plus h. No brainer. And then minus the quantity f of x plus g of x. Ooh, getting over here in the margin, all divided by h. Now, look, I've left the notation of derivative, and now I'm in the notation of limits, which means I can use my limit laws. And the limit laws say that the limit of a sum is the sum of the limits. So I can start playing games with all this, right? So I end up with the limit as h goes to 0. I'm going to collect these two guys, and I'll get f of x plus h, excuse me, minus f of x. Right? And then I'm going to collect these two guys plus g of x plus h. Now, really all I'm doing here is I'm using a combination of commutative and associative properties to get rid of parentheses. And then the whole thing is over the common denominator h. Right? Common denominator, relatively huge. So if it's common denominator, that means I can steal it, and I'm going to use the property that the limit of the sum is the sum of the limits. I'm going to bust this up into two limits. So this becomes the limit as h goes to 0 of f of x plus h minus f of x over h. I grab the common denominator, which is common to both, plus the limit as h goes to 0 of g of x plus h minus g of x all over h. And hush my mouth, what's that equal to? Well, this guy is the definition of that, and this guy is the definition of that, and guess what? The derivative of the sum. Now, if I want to be consistent in my notation, it is the sum of the derivatives. And there's nothing to it. Isn't that fun? Now, really think about it. There's no such thing as subtraction. It's just addition with negative numbers. So I know, using without loss of generality, in other words, using the exact same logic, excuse me, I know that the derivative of a difference, so f of x minus g of x, is equal to the difference of the derivatives. We're not going to go through the proof because you guys probably want to punch me in the head. All right? And I don't like to get punched in the head by my students. That's it. All right? That is, excuse me, that's the last of those kind of cutesy little rules, let's call it. So, now, the last of these, your author chooses to use a very interesting way to prove this, and we'll actually do it with our calculators in class. We're going to explore this thing. I'm just going to give you the rule and then I'll be done with it, okay? The last of these is that the derivative, it's a wonderful piece of information, and we'll prove it in sort of in greater algebraic process down the road. It's simply this. The derivative of e to the x is equal to, you ready? E to the x. E to the x is one of the only functions that is its own derivative, other than 0. The derivative of 0 is 0. Derivative of e to the x is e to the x. Now, the reason that your author does the strangest things, I'm going to put this in red, which means if you use this as an example, this is the color of the pen I'm going to use on your work just to scream at you. He defines e as being the number such that this e to the h minus 1 over h is equal to 1. That's how he defines e. It's not specious arguing, but it seems so contrived as to almost be silly. All right, really, the bottom line is I want you to remember that the derivative of e to the x is equal to e to the x, and trust me, you will not be able to forget it. Now, combined with all of these rules that I just laid down before you, you're going to be doing a ton of derivatives. You're going to be very good at taking derivatives, all right? But you need to know that these derivatives, these rules of differentiation are going to be taken in combination with each other. You're going to constantly use them, and you just have to get fluent at them. I am looking for fluency. Fluency means you can do them without thinking about them, okay? All right, right on. Well, I hope you enjoyed. I'll see you tomorrow in class or at the next class meeting. Have a great day.